So, in this chapter, we're going to talk about the chemistry of benzene and specifically the electrophilic aromatic substitution reaction. And this, surprisingly, is the first chapter in Organic 2 where we get to reactions. However, pretty much the rest of the chapters in this course are going to involve reactions. And in the chapters that involve reactions, I use the lecture slides, the PowerPoints, relatively little, and I'm going to use the whiteboard, which is just a camera pointed at a piece of paper, relatively a lot. It's going to be super important that you take notes of what I write on the camera and write these things down. Part of organic chemistry is learning, memorizing, for lack of a better word, the reactions. And if you write them down, that will happen faster. That being said, I'm also going to look at several mechanisms in this chapter, and we're going to look at many mechanisms throughout the rest of this course. And what you're going to find is that there's commonalities in these mechanisms. Where is the electron rich thing? Where is the electron deficient thing? How do the electron rich and the electron deficient thing interact with each other? And we call these things electrophiles and nucleophiles. And what we're going to look at is how these interactions occur. And what you'll start to see is, especially if you write these things out, you're going to start to see patterns. And that's how you can truly learn organic chemistry as opposed to, memorize 500 reactions. So let's take a look here at some of the reactions of benzene. And in this first section, what we're going to start with is the bromination reaction. So the first thing I want to present is just the reaction in general, and then we'll look at how this reaction occurs. So if we take a benzene ring, okay, just plain old benzene, no substituents. Remember, we talked if we have an OH, it's a phenol, or if we have a CH3, it's called toluene, and so on and so forth. Here we just have plain old benzene. If we add bromine and FeBr3 as the catalyst, what we can make is the benzene ring with a bromine and HBr. Okay? So, in this case, we have what is called an electrophilic aromatic substitution reaction. Remember that in this benzene ring, before we start the reaction, there's a hydrogen here, okay? And at the end of the reaction, we have substituted this hydrogen with a bromine, and we get, because remember this is Br2, we get an H and a Br left over. And again, this is a catalyst. It's involved in the reaction, but it isn't used up in the reaction, which is making it a catalyst. So this is a substitution reaction. This reaction involves the electron-rich pi bond of this benzene ring acting as a nucleophile, so the ring is the source of electrons, attacking a Br plus, which is formed from the reaction with FeBr. And this Br plus is acting as a electrophile, which is why it's called electrophilic aromatic substitution. The electrophile is the thing that the ring is reacting with. The ring itself is acting as a nucleophile. Remember, nucleophiles are electron rich, oftentimes negatively charged, although there's no full negative charge here. Electrophiles are electron deficient, oftentimes with a positive charge, and as we look at the mechanism of this reaction, what you're going to see is bromine actually does have a positive charge. So this is basically what we're doing in an electrophilic aromatic substitution reaction. In this particular case, we're substituting bromine and hydrogen in order to make this type of compound. So let's look at how this actually works. Said another way, let's look at the mechanism of this reaction. So let's start with Br bonded to Br. Okay, so Br2, but written as a Lewis structure instead of just Br2. And what we're going to react it with is the catalyst here, FeBr3. Okay, and basically one of these bromines is going to interact with the iron. And the iron interacts as a Lewis acid or an electron pair acceptor. So essentially what happens is this interacts with the iron. All right, so these electrons leave with this bromide. So you basically lose Br minus. And what we end up with is Br. Okay, I'll just write it this way. We don't need all the lone pairs. We end up with Br plus and FeBr4 with a minus charge. This, not organic chemistry, not super important. But what it shows us is that we have Br plus. Remember, electrophiles are things that want electron density and are often positive. Now, they don't have to be positive, but they often are positive. So now we have an electrophile. So now we can interact that with our benzene ring. And notice when I'm drawing the benzene ring in mechanisms, I have to draw the 3 bonds instead of the circle, because this bond, this pi bond, is the source of electrons. This is the nucleophile, this pi bond, just because it's going to happen to be physically closest to the this one. All right, so we're going to have Br plus FeBr4 minus. All right, so when I say it's physically closest, just by the way it's drawn, this electron density acts as the nucleophile and attacks the Br plus electrophile. What do we get? Well, when that happens, what we get is this double bond breaks. We get a Br here and an H here. Remember, there's still an H here, right? Because there's one H at each of these carbons. So there's still an H here. So now we have 3 bonded carbon, and the charge on that 3 bonded carbon is plus. So we have a positive charge on this carbon. Now, you may have seen that I drew this bracket here, which is going to indicate resonance. So I'm going to draw the resonance forms of this. This can resonate. So what happens is this moves over here, and we get a second resonance form. Okay, where now the double bond is here, and that double bond's unchanged, and this Br and this H are unchanged. But now this is the 3 bonded carbon, right? Because the other bond is to a hydrogen. So now the plus is here, so the plus has resonated. And if we do it one more time, we can move that bond over. And what we end up with is now this bond is down here. This bond is still where it was. The Br and the H are still where they were, and the positive charge is here. So we've moved that positive charge, or we've resonated that positive charge throughout the ring. So there are 3 resonance forms formed here. And in many times and throughout this lecture of this whole chapter, I'm going to draw these 3 resonance forms, but other times I'm going to skip it because it gets redundant. So if we remember back to the previous chapter, this molecule undergoes a electrophilic aromatic substitution because we want to regain aromaticity. Well, how are we going to regain aromaticity? Well, the way we can regain aromaticity is to lose this H. All right, we want to lose this H because this H has electron density. So if we lose this as H plus, this electron density could jump in and refill the double bond. So what do we have in here that can help us to do that? Well, we have FeBr4 minus. So this can attack this, and this bond can drop there. And when we do that, we regain the aromatic ring, which is important, remember, because this is especially stable. Let me move this up a bit. So this is especially stable, and we end up with the Br here plus HBr plus FeBr3 if you prefer, because that's just basically showing that it's the catalyst. We had it at the beginning, and if you want, we get FeBr3 again. No one really cares, I guess, if you write this. I mean, it's technically correct that you put this here because then you show it at the beginning and the end. So therefore, it's a catalyst. But, not super important. So the electrophilic aromatic substitution involved an electrophile. This electrophile happened to have a discrete positive charge. Okay. We also had, of course, a nucleophile, and the nucleophile was the pi bond of the benzene ring. After this attack occurred, we were able to find a positive charge on this carbon because it was a 3-bonded carbon. Remember, there is one H that's not shown here. Okay, so we got a 3-bonded carbon, so it had a positive charge, and that positive charge could resonate completely throughout this ring. However, this molecule really wanted to be aromatic. So this proton becomes relatively acidic, if you will, because if this molecule loses this proton, the aromaticity is regained. So there's something in here, a base, that can take away this proton. And in this case, the base is Br minus, which, as you probably know, is not a very strong base, but this is a pretty acidic proton that wants to leave because we regain aromaticity. And basically, we're able to take this proton off. We regain the aromaticity, and we get the HBr product. At the end of the day, H was originally here, Br is now here, and this is the overall reaction. So this is basically how this works. Now, one thing I need to show you is, what about the rate of this chemical reaction? And this gets back to some thermodynamics/kinetics that you have learned in general chemistry. Let's look at an alkene example and a benzene example. Remember that the rate of a reaction depends on the activation energy. And that is the difference between the starting material and the transition state that you're going to find up here. And then down here, you would find intermediates if there was intermediates in the reaction. So in this case, the difference in energy of benzene to the transition state is much greater. Said another way, this has a higher activation energy than for an alkene. Why does this occur? This occurs because alkenes are relatively unstable compared to benzene. So since benzene is so stable, it starts at a lower energy. And when it starts at a lower energy and it still has to move up to a, transition state that's relatively unstable, the difference is very great. Remember that rates of reactions depend on their activation energy. So if the activation energy is greater, the reaction goes slower. So relatively speaking, these are slow reactions because of this greater activation energy. Now, this is not a physical chemistry course, right? So we're not going to go into great detail or ask you on a test to explain this difference in activation energy. But at the same time, it does allow you to understand how reactions are going. It especially allows you to understand how reactions are going when there are competing reactions, because the differences in energy explains the rates. And if there's competing reactions, the one that goes faster wins. So it is important to point out, but again, not something that's going to be put on the test. In the next section, we'll look at some other reactions of electrophilic aromatic substitution involving benzene. So in these types of reactions, bromine is not going to be the only thing that can substitute that hydrogen. So let's look at some other examples which are going in the same way. For some of them, I'll draw the entire reaction mechanism, including the resonance forms. But for others, we'll skip the resonance forms because, they get old. You're drawing the same thing over and over and over again.